Today, we're going deep inside design. We're opening up Chapter 3, the Grid-Connected PV Plant Design session. If you're looking to really demystify the complex world of utility-scale PV plant design, well, you're in exactly the right place. We're moving way beyond basic theory and diving headfirst into the engineering reality. We're going to break down exactly how a massive, grid-connected solar power plant goes from just a simple utility bill to a fully functional megawatt-scale powerhouse. And we're doing it by dissecting a real-world case study. So grab your notebooks because this is going to be fascinating.
All right, here's our roadmap for today. 1. Sizing PV by consumption. 2. The 4.1 megawatt P Sphinx project. 3. Step-by-step equipment sizing. 4. Power factor correction sizing. And 5. Delivering the engineering package. Let's dive right in.
Section 1. Sizing PV by consumption, starting with the bill.
So let's start with the absolute foundation of our design process. Because contrary to what some folks might think, a great utility-scale PV plant doesn't just start with someone drawing solar panels on a map. So ask yourself, before a single line is drawn in AutoCAD, before you even look at a module datasheet, how do we actually begin? What's the trigger that sets this whole engineering machine in motion? Well, it usually comes down to two main starting points. First up, you've got the available area method. This one's pretty straightforward. You've got a specific plot of land or a roof, and your goal is literally just to pack as much generation capacity into that physical footprint as you possibly can. But for large commercial and industrial facilities that operate under a net metering scheme, we generally lean on the other approach, the consumption method. See, because the grid essentially acts like a giant battery under net metering, we can just look at the client's annual energy bill, pinpoint their exact energy demand, and mathematically work backward. We account for all the inherent system losses to figure out the exact size that solar plant needs to be to offset that specific load. Let's break down how this actually builds mathematically. This is the absolute core of the consumption method. Step 1, you take the total annual bill, divided by the utility tariff, and boom, you've got the average AC energy demand in kilowatt hours. Okay, step 2, we have to account for the fact that converting DC power from the panels into AC power for the grid isn't 100% efficient, right? So we calculate the required inverter DC input by factoring in the inverter's efficiency, which usually sits right around 98.5%. And finally, step 3, we find the absolute raw DC power needed, the PV nameplate capacity. We do this by dividing by the performance ratio, or PR, which basically accounts for all those real-world losses like shading, temperature, and cable resistance. Follow these steps and you've got the exact megawatt requirement needed to totally neutralize that utility bill. Section 2. The 4.1 MWP Sphinx project, a real-world case study.
Now, textbook theory is great, but seeing it actually applied, that's where the real magic happens. This project boasts a total DC capacity of 4.1 megawatts peak, which translates to roughly 3.6 megawatts of AC grid power. Just to put that into perspective for a second, this isn't some rooftop residential setup. This is serious, heavy-duty, utility-scale infrastructure built to power a major industrial operation, day in and day out.
And to handle that massive 4.1 megawatts of raw DC power pumping in from the sun, the Sphinx project uses a seriously formidable lineup. We're talking 30 individual Huawei 115 kVA inverters. These guys are the absolute workhorses of the plant, constantly syncing and converting that raw DC voltage into nice, usable, stable AC power. But here's the catch. We can't just pump that power straight into the utility grid as is. The plant's architecture is actually split across two independent, heavy-duty transformer stations. Each of these stations is rated at 2 megavolt amperes. Their entire job is to step up that low voltage coming from the inverters all the way up to the 11 kilovolt medium voltage that the local utility network demands.
Now, take a look at the specific engineering parameters they chose here. As we mentioned, they're stepping the 0.4 kilovolt inverter output up to an 11 kilovolt grid connection. They're using a DIN 11 vector group, which, if you know your transformers, is absolutely crucial for handling unbalanced loads and trapping harmonic currents. It keeps the power profile super clean. Plus, they're using ONN cooling. That stands for oil natural, air natural. Basically, it means these transformers are robustly designed to passively cool themselves right in the middle of the scorching Egyptian desert without having to rely on mechanical cooling fans that could eventually fail. Every single detail here is meticulously chosen to safely and efficiently bridge our solar array straight to the grid.
Section 3. Step-by-step equipment sizing, down to the wire.
Okay, so with the macro-level architecture locked in, we need to zoom in and make sure the actual solar panels and inverters are perfectly matched. And the absolute most vital metric in this phase? The DC to AC ratio. That's the total installed DC capacity of your solar panels divided by the total AC output capacity of your inverters. Now, you almost always want more DC power than AC power. Why? Well, because panels almost never operate at their peak laboratory conditions in the real world. By oversizing the DC array, you're making sure the inverter is working at full capacity for way more hours out of the day. For the Sphinx project, sitting out there in a super high irradiance environment, they meticulously landed on a ratio of 1.18. It's the perfect sweet spot to maximize energy yield while minimizing clipping losses, which, of course, is what happens when the panels produce more power than the inverter is legally allowed to accept.
When we break down the exact configuration used on the Sphinx site, it is just a beautiful harmony of electrical engineering. They went with 620-watt peak, high-efficiency modules. By daisy-chaining exactly 20 of those modules together into a string, they hit the optimum input voltage window of those Huawei inverters perfectly. And that holds true whether it's a freezing cold winter morning or a blazing hot summer afternoon. From there, they land 11 of those strings onto every single inverter. Finally, all that precise power generation is routed out through massive, heavy-duty 3-core, 120 square millimeter aluminum medium voltage cables.
I actually want to pause for a second on this core engineering philosophy right from our source material. Sizing is never just guesswork. Math is your map. It gets you in the right territory, but software simulation tools like PVsyst, well, those are your compass. You absolutely must mathematically validate your string lengths against those extreme temperature coefficients, and then you simulate the whole year to make absolutely sure your chosen DC to AC ratio is going to generate the financial returns you're expecting.
Section 4. Power Factor Correction Sizing. Now this topic right here, this is what separates the amateurs from the pros. When you're connecting a massive power plant to the national grid, you aren't just pushing raw power. You've got to play nicely with the grid's rules. We have to ensure our plant provides not just active power, the stuff doing the actual work, but also reactive power, which the grid desperately needs to maintain its voltage levels. So step 1, we define our active power target. Step 2, we calculate exactly what the inverter has to output to hit that target while also overcoming all the transformer and cable losses. Step 3 is where the heavy math kicks in. We calculate the required reactive power, which we represent with Q, based on the power factor demanded by the grid. And finally, step 4, we take that total required reactive power and compare it directly against what our modern, smart inverters can actually natively produce on their own.
And here is the real-world consequence of all those calculations. If the grid operator demands more reactive power support than your 30 inverters can safely provide while still pushing that active power, well, you've got a deficit. And you can't just ignore it. You have to actively design, size, and install physical, external compensation hardware. We're talking localized capacitor banks or dynamic STATCOM systems to bridge that gap. Doing this ensures your PV plant acts as a compliant, stable, and genuinely helpful generator for the grid, instead of a disruptive one.
Section 5. Delivering the engineering package. All right, so we've run the load profiles, we've sized the modules, the strings, the inverters, the transformers, and we've nailed down the power factor correction. Now we have to translate all of that highly complex math into actionable blueprints. Here is the precisely scaled physical footprint of the Sphinx project's 4.1 megawatt peak array. It essentially translates our string sizing, remember those groups of 20 modules we talked about, directly onto the physical terrain. It perfectly accounts for row spacing so one row doesn't cast a shadow on the next during the low winter sun, and it strategically places those transformer stations to keep the length and the cost of those expensive DC cables to an absolute minimum. And right behind that physical layout is the plant's electrical nervous system, beautifully mapped out here in the single line diagram, or SLD. Now this isn't just some rough sketch, it's a wildly precise electrical schematic. It shows exactly how the power from those 115 kVA inverters routes directly into the main distribution panel, flows through these massive 4-pole motorized circuit breakers that are designed to handle thousands of amps, and integrates perfectly with the surge protection devices before finally making its way up to those medium voltage transformers.
But honestly, what we've just looked at is only the tip of the iceberg. To actually get a massive project like this approved for construction, an engineer has to submit the Complete Base Design Engineering Deliverable List, or EDL. This whole comprehensive package is what proves the plant is safe, compliant, and totally optimized. It's got everything: the structural civil drawings, the single-line diagrams, exhaustive mathematical proofs for all your cable sizing and voltage drops, the rigorous PVsyst yield simulation reports, life-saving earthing and lightning protection layouts, every single component datasheet, and a massive line-item bill of materials. The whole shebang is in here. A complete design really is a rigorous, undeniable body of evidence.